Welcome back, everyone, to another deep dive. We're picking up where we left off, exploring AI and privacy. Specifically, you know how to make sure your sensitive data stays safe when you're using these powerful models.
It's a challenge that's only getting more and more important.
Totally. And today we're looking at a new technique. Um, it's called Equivariant Encryption.
Equivariant encryption, yeah.
EE for short, of course. And it's all laid out in this research paper from NISA Research. Have you had a chance to look at this one?
Yeah, I've had a look. It's pretty fascinating stuff.
It is. The core concept is kind of mind-blowing when you think about it. We're talking about running an AI model without it ever actually seeing your raw data.
It really changes the game for privacy in AI.
That's the promise of EE. So to kind of set the stage here, the paper starts off by talking about existing privacy tools. Things like differential privacy, secure multi-party computation, and homomorphic encryption.
Right, the usual suspects.
Yeah, exactly. But to be honest, those always sound a little intimidating to me. Can you break those down for us a little bit?
Sure, let's start with differential privacy. So imagine you are adding like a blur to a picture.
Okay, yeah.
You can still see the general shapes,
Right, get the idea.
but the details, the individual details are kind of obscured. So that's great for protecting the source of the data, like a big data set,
Right.
but not necessarily for individual records, especially when a model is actually using the data.
So it's like protecting the ingredients, but not the actual dish itself.
Kind of, yeah. It's more about protecting the overall patterns in the data rather than the specific individual data points.
Gotcha. Okay, that makes sense. What about secure multi-party computation? That one sounds intense.
Yeah, this one's a bit more complex. Imagine a group project, like back in school, where everyone only has a piece of the puzzle.
Okay, yeah.
No one person actually sees the full picture until the very end when you put all the pieces together. So it's a good way to collaborate.
Without having to fully trust each other.
Exactly. But it can get really complex and slow, especially when you're talking about AI, and especially these large models that just gobble up data.
Yeah, you need things to move quickly.
Exactly. You need efficiency.
Okay, so we've got blurred pictures and group projects. What about homomorphic encryption?
Now, this one is pretty cool. This one lets you do computations on the data without actually decrypting it first. So imagine being able to analyze medical images, but they're still encrypted.
Wow.
So you get the insights you need, but you maintain patient privacy throughout the whole process.
So the data is never actually exposed.
Exactly. The downside is that it requires a ton of computing power.
I can imagine.
It can be quite a challenge to implement in a practical way.
Right. Okay, so it seems like we've got some really interesting methods here, but they all have these trade-offs. Is there a way to kind of get the best of both worlds, strong privacy and high performance?
That's the million-dollar question, right? And that's where equivariant encryption comes in. It's like instead of locking everything up tight, like with homomorphic encryption.
It's more like creating a secret code language that only your AI model understands.
Okay, interesting.
So you're transforming the data into a format that the model can use, but it's completely unreadable to anyone else, even if they were to somehow get access to it.
So instead of a lockbox, it's more like a sophisticated translation.
A very good analogy. And what makes it so efficient is that it focuses on specific layers within the AI model, the layers that are most vulnerable to leaking information.
So it's like targeted scrambling.
Exactly.
Yeah.
And by doing that, they can achieve near zero latency overhead, meaning it's really fast.
So it doesn't slow things down.
Not at all. In some cases, it can even be faster than running the model without any encryption.
Wow, that's impressive. But okay, if it's so fast, how secure is it really? Could someone crack the code and actually see the original data?
That's where the complexity of the transformation comes in. They use these high-dimensional transformations, which would be computationally incredibly expensive to reverse engineer.
So like creating a puzzle with billions of pieces. Exactly. Good luck trying to solve that.
Okay, so brute force is out of the question. Now, the paper also mentioned some specific use cases for EE. Where would this be particularly useful?
They highlight LLMs, the large language models, vision models, and something called retrieval augmented generation, or ARG.
Lots of acronyms to keep track of.
I know, but the point is, imagine using a chatbot, but it never actually sees your words, or analyzing medical images in the cloud with complete privacy. That's the kind of power we're talking about.
That's pretty remarkable. I could see how this could be a game changer, especially in fields like healthcare and finance. But it could also impact how we use AI in our daily lives, right? Just knowing that your data is truly protected.
It's a huge step forward in responsible AI development.
Absolutely. because no system is perfect.
Yeah.
And the paper does talk about potential threats to EE as well. What should we be aware of?
Well, they focus specifically on LLMs and how an attacker might try to guess the original tokens, those units of text, just by observing the encrypted input and output.
So even with this advanced encryption, there are still things to watch out for.
Right. It's like a constant arms race between security and those who are trying to break it.
Always staying one step ahead.
Exactly. But the researchers didn't just identify these attacks. They actually went a step further and provided benchmarks comparing EE with those traditional methods we talked about earlier. They measured things like fidelity, meaning how accurate the model remains,
Right.
and latency, so how fast it runs.
How did it do? Was there a trade-off?
The results were really promising. EE maintained high fidelity, meaning the model's performance was still accurate even with the encryption. And remember how we talked about that near zero latency? Well, in some cases, EE achieved negative latency overhead.
Wait, negative?
Yeah, meaning it was actually faster than the unencrypted methods.
That's incredible. It sounds like E is really living up to its promise, delivering both privacy and performance.
It's a very exciting development.
It really is. So we've covered the basics of EE and kind of how it stacks up against those traditional encryption methods. But why does this all really matter? We'll delve deeper into that and explore those real-world applications in the next part of our deep dive. Stay tuned.
Welcome back.
So last time, we were talking about how equivariant encryption could be a game changer for AI privacy.
Right, a huge step forward.
But, we also touched on the fact that no system is perfect.
Right, there's always going to be challenges.
Exactly. There are always going to be those vulnerabilities. And that's why the researchers at NASA actually dedicated a whole section of their paper to just analyzing these threats.
They did a really thorough job of trying to anticipate potential attacks.
Yeah, they really did. They focused specifically on attacks that target LLMs, large language models. What makes LLMs different from other AI models when it comes to security?
Well, it all comes down to how LLMs process information. So they break down text into these individual units called tokens. Think of them like words, or sometimes even just parts of words. And then each token gets converted into a numerical representation, something that the model can actually understand.
So the model isn't seeing the actual words, it's working with these numerical tokens instead.
Exactly.
That makes sense for processing language, but how does that relate to security?
Well, the problem is that if an attacker can figure out the mapping between those tokens and the original text,
Ah, I see.
they could potentially decrypt the entire conversation. Even if the inner workings of the model are protected by E, the input and output could still be vulnerable.
So the model itself isn't leaking information, but the data going in and out could be compromised.
Right, exactly. It's like if you have a secure room, but the doors are left wide open.
It doesn't really matter how secure the room is.
Exactly, and that's what the NASA researchers wanted to address with their threat analysis.
And they call these baseline attacks, right? What are those exactly?
Yeah, so think of these as the most basic, straightforward attack methods. Kind of the first things an attacker might try when they're trying to understand a system's vulnerabilities.
So it's like testing the defenses with the most common tools before you move on to more, sophisticated attacks.
Exactly. Start with the basics. So one example is a brute force attack. The attacker just tries every possible token combination until they find the right mapping.
So like trying to crack a password by just randomly guessing letters.
Pretty much. It might work eventually, but with large vocabularies, it quickly becomes impossible. It would take forever.
Way too long.
Way too long. So then there's random sampling. That's where they just randomly select a set of tokens and try to match them to the original text. Less resource intensive than brute force,
Right.
but also less likely to succeed.
It's a gamble.
Total gamble. And then there's hill climbing. This is where the attacker starts with a random mapping and then they make small changes, trying to get closer to that correct decryption with each step.
So like climbing a hill, trying to reach the peak,
Yeah.
which would be that correct mapping.
Exactly. A great way to visualize it. The problem is they can get stuck. They might think they found the best solution, but there's actually a better one out there.
So it's like thinking you've reached the top of the mountain when there's a higher peak hidden behind the clouds.
A perfect analogy.
Okay, so these baseline attacks, they might seem simple, but they highlight the real challenges of securing LLMs with EE.
It's like laying the foundation for understanding more advanced attacks. If even these simple methods can pose a threat, then we need to be really clever about how we build defenses.
So how are e-developers fighting back? What are they doing to build a more secure future for AI?
Well, one key defense is using what we call high-dimensional transformations.
Okay, what's that?
It's essentially taking that token mapping and making it much, much more complex. Think of it like going from a simple three-number lock to one with like a million numbers.
Wow. Okay.
Brute force suddenly becomes impossible.
Like making a password way longer and more complex.
Exactly. It's the same principle. By increasing the complexity of that mapping, they make it exponentially harder for an attacker to reverse engineer the encryption.
So it's like a puzzle with billions of pieces instead of a few hundred.
A great analogy. This makes brute force and random sampling pretty much useless. And even hill climbing becomes way more challenging because the search space is just so vast.
So it's not just about making the encryption stronger. It's about making the attack itself way more difficult. So difficult that it's not even worth it for the attacker to try.
That's a core concept in cybersecurity. You don't necessarily need to make your system impenetrable. You just need to make the cost of attacking it way higher than the potential reward.
It's like putting a really tall fence around your property. Someone could still climb over it if they were really determined,
Right.
but it's going to take a lot of effort.
Exactly. And that's what these high-dimensional transformations are doing.
Okay, that's a really interesting approach. But I imagine there are other defenses in play as well, right?
Oh, definitely. High-dimensional transformations are powerful, but they're not the only tool. Researchers are also exploring other techniques like introducing randomness into the encryption process.
Randomness. How does that help?
Think of it like shuffling a deck of cards. Even if you know the order of the cards before they're shuffled, it's much harder to predict their order afterward.
So it's like adding unpredictability to the encryption.
Exactly. It throws off the attacker. By introducing these random elements, it makes it much, much harder to find patterns or exploit weaknesses in the algorithm.
So even if they understand the encryption method in general, the specific implementation is always changing. It's like a moving target.
Right. It throws a wrench into their plans.
That sounds super effective.
Mm.
But I'm guessing there are trade-offs here too, right? Could adding randomness impact the performance? Make
Yeah.
things slower?
That's a good point.
Yeah.
Anytime you add complexity to a system, there's potential for performance overhead. But researchers are working to minimize those trade-offs.
So it's a balancing act.
Exactly. Finding that sweet spot between security and performance.
This is all really fascinating.
Hmm.
It's like watching this chess match unfold between the people developing these defenses and the attackers.
It's a really dynamic field, and it's only going to get more important as AI becomes more and more integrated into our lives.
Right, absolutely.
Yeah.
So we talked about the potential threats to EE and some of the defenses being developed. But E isn't just about protecting data. It's about like unlocking the full potential of AI in a way that respects our privacy.
Exactly. It's not just a security measure, it's an enabler. EE lets us explore all these new possibilities with AI without having to compromise our values.
And that brings us to the next part of our deep dive. We're going to explore those real-world applications of EE and the impact it could have on various industries. Welcome back to the deep dive.
Yep.
So we've explored what equivariant encryption is, how it works, all of that. But now I'm really curious about the real-world implications. Where does this actually make a difference?
That's the exciting part, right? EE isn't just some theoretical idea. It has the potential to change industries, to really change how we interact with AI every day.
The researchers at NASA, they highlighted some specific use cases in their paper. One that really stood out to me was using EE with large language models, LLMs.
Yeah, LLMs are everywhere now. We're seeing them in chatbots, virtual assistants, all sorts of creative tools.
It seems like every day there's a new LLM application.
Yeah.
But they all rely on these massive amounts of data, and that makes me think about the privacy implications.
For sure. Think about it. You're using a chatbot to discuss something sensitive like your medical history. It's a little unnerving to think that information might be vulnerable.
Yeah.
That's where EE could be huge. Imagine that chatbot can process your requests, give you responses, without ever actually seeing your raw data.
So you could have a truly private conversation with an AI.
Exactly. And it's not just about personal privacy either. Think about companies using LLMs to work with confidential documents, sensitive customer information. EE could provide a level of security that we just can't get with traditional methods.
It's like having this virtual vault for your data, where only authorized people can access it.
Perfect analogy. And it's not limited to LLMs either. The NASA paper also talked about the potential for computer vision models.
Now, this is where it gets really interesting for me. Computer vision is everywhere. Healthcare, security, self-driving cars. The privacy concerns are huge.
Right. Imagine a hospital wants to use AI to analyze medical images. With E, they could share those images with specialists all over the world without compromising patient privacy.
Or a self-driving car navigating through a city. It could be processing all that visual data from its surroundings without actually recording or transmitting any personally identifiable information.
Exactly. It really opens up some amazing possibilities in all sorts of fields.
It's like AI can see without seeing. It can use the information it needs without actually accessing the raw data.
Right, and that brings us to another interesting use case, something called retrieval augmented generation, or R.
Now, RAG, that one's a bit new to me. What is that exactly?
So RAG combines LLMs with these external knowledge sources like databases, documents, even just information from the internet.
So it's like giving the AI access to this huge library of information.
That's a great way to think about it. It lets them access information that goes way beyond just their initial training data. And this is huge for areas like research, education, customer service. Think about an AI assistant that can answer your questions by drawing on a vast amount of information.
That sounds incredibly powerful. But, once again, we have to think about those privacy concerns. If this AI is pulling from all these external sources.
Especially if some of that information is sensitive.
Exactly.
Well, EE could be the answer. With EE, the AI can use that information without ever actually exposing the raw data itself, either to itself or to anyone else.
So it's like having a privacy filter built right into the AI search engine.
Yeah, it can find what it needs without putting anyone's privacy at risk.
Okay, so it's clear that EE has this enormous potential, all these applications. But I'm sure there are challenges too, right? With any new technology, there are always going to be hurdles to overcome.
Absolutely. Scalability is a big one. EE works really well for smaller models, but as AI systems get more complex, that computational overhead can become a bottleneck.
So the encryption needs to evolve as the models get bigger.
Exactly. Researchers are working on this, coming up with more efficient EE algorithms that can keep up with the rapid advancements in AI.
It's like this constant race, right?
It is. And then usability is another challenge. Right now, EE requires a fair amount of technical expertise to implement, so it's not something everyone can easily use.
So there's still a barrier to wider adoption?
For now, yeah. But people are working on it. There are tools and frameworks being developed to make EE easier to use.
So hopefully one day we'll see EE become as common as, using the internet today. Something that anyone can use.
That's the goal, to democratize AI privacy, give everyone the ability to protect their data.
Well, we've covered a lot in this deep dive, I have to say. We've explored all the ins and outs of EE, the potential benefits, the challenges, and really, the amazing possibilities this opens up.
It's exciting to see where this technology goes.
It really is. And, the takeaway here for me is that secure AI isn't just a pipe dream anymore. Innovations like EE are making it a reality.
Exactly. AI is going to continue to change the world. It already is. And it's reassuring to know that there are people out there who are committed to protecting our privacy along the way.
That's a great note to end on. Thanks for joining us for this deep dive into the world of equivariant encryption.
It's been a pleasure.
And to our listeners, thanks for tuning in. We hope you've enjoyed this exploration of AI privacy. Until next time, stay curious.